This example illustrates how to create a validator platform model and how to set up the application source code to be executed in conjunction with this model. The platform model is specified with the Ovid graphical editor, which provides a library of generic components modeling behaviors of common hardware parts such as interrupt controllers, timers, and CAN bus controllers. Additionally, Ovid provides automatic OSSEC configuration from given OIL files. Ovid stores the platform model of XML format and generates C code for interface with the application software. The user can define new components in Ovid. Moreover, library components can be redefined by adding more detail, thereby making the model as close to the hardware as desired. Execution time estimates are essential for platform-aware simulations. Chrona's time extractor tool constructs a database with execution times at a certain level of granularity, which is automatically determined based on the structure of the application software. Setting up the application software to be executed on the validator platform model is done based on aspect-oriented programming principles, where the platform-related aspects are weaved with the application source code. The relevant point cuts are determined by the time extractor tool. Execution time estimates are embedded in the code with the time weaver tool, such that the execution time between 2 points in the code can be computed at runtime, based on the actual execution path taken during simulation. The Platform Weaver tool ensures that calls to operating system services and direct accesses to hardware components are routed to the platform model during simulation. Let us specify now an example of a platform model in Ovid. We start out with an Eclipse project containing the C code of the control application. This contains several C functions corresponding to OSSEC tasks and interrupt service routines. The platform model triggers executions of application code, while the application may interact with the platform model by calling OSSEC functions and by directly accessing hardware registers mapped by memory locations. We use Chrona's Ovid tool to create a new platform model as follows. The OSSEC configuration is found in the OIL file in the platform folder. We can create here a new Ovid file. The platform model can be created graphically by dragging components from a library and dropping them on a canvas, setting properties of components, and connecting components via ports. We start by instantiating a CPU scheduler component, which models one computational core together with an OSSEC implementation. This component has a generic input port, which in this example will be used to receive interrupts. Let us add now two more components: an interrupt controller and a Simulink bridge. The latter will be configured to exchange input and output data with the Simulink model of the vehicle. We connect the output port of the interrupt controller to the interrupt port of the CPU scheduler. Now we define the input port of the interrupt controller to represent an external interrupt pin. We rename it to the IRQ1, and we add some new properties representing default configuration. We can select the port directly from the outline view, which is especially helpful for navigating complex models. We specify the valid edge of the interrupt, as well as the name of the associated interrupt service routine. Let us add a new interrupt port in which the interrupt controller will receive requests from on-chip peripherals. In the Simulink bridge, output ports represent sources of interrupts. We rename the default port and connect it to the external input of the interrupt controller. Let us continue with the configuration of the CPU scheduler component, which can import OSSEC settings automatically from OIL files. We import here the OIL file from the platform folder. We can see now the list of OSSEC tasks and their properties, as well as the list of interrupt service routines. The platform modeling is continued until a full platform model is achieved. The tasks and interrupt routines in the OSSEC configuration correspond to functions in the application code that are easily reachable directly from the Ovid model. Let us jump to the source code of an application function. The validator is able to carry out, logically, concurrent executions of application code that closely match the executions on the target hardware. This includes preemptions and execution times, which need to be estimated for a specific granularity of source code. This is the job of Chrona's time extractor tool, which determines execution time estimates of fragments of application code based on a number of estimation methods. The granularity of code fragments for which time estimates are necessary is determined automatically based on the structure of the application code and on the system configuration. The tool has a plugin architecture, allowing different estimation methods to be employed. Chrona offers a time tracer plugin, which processes real-time execution traces obtained from actual executions on the platform. Other plugins are available for processing results obtained by third-party tools, such as Absinth's WCET Analyzer tool or UC Berkeley's Game Time tool. Let's run the time extractor tool on our example system. The tool determines first the places in the code where platform behavior needs to be executed. By default, these are all the source lines with access to global variables used in different tasks or to hardware registers. The user can specify different rules in this respect. Then the time extractor tool determines execution time estimates based on the results of the time tracer plugin. These are the inputs to the time weaver and platform weaver tools. In the current validator version, weaving is done automatically by instrumentation at the source code level. The instrumentation generated by the time weaver keeps track of execution time as the code executes during the simulation, while the one performed by the platform weaver is responsible for synchronizing code execution with platform model execution. Here we can see an example of the instrumented code. This setup results in the fast simulations of the platform and application software containing the main characteristics of executions on the real hardware, such as preemptions, executions, and communication times. Thank you for your attention.